Hello everyone, it's August 21st. It's very late. It's 10:56 p.m. Am I delaying today because I'm dreading Saturday? Not really, but maybe a little bit. Anyway, I had other obligations today. I was publishing a beta testing version of an app earlier today. And the thing is, when you write an app, when you write a project, whatever you do, you test, you test. Honestly, I didn't test for this thing, but like you prepare, and you feel like okay, everything's ready. I'm gonna push for a beta testing, and then just the last moment when you're about to push, and then bugs and troubles just start showing up. Like things you thought it's all good, like the design pattern you had in the past, it all makes sense, and suddenly at this moment, when the beta is out for testing, you realized everything that made sense in the past did not make sense anymore. Like, why did I design things that way? And I thought it made sense, but now it did not make any sense. Then you start changing, right? You start, convincing yourself, yes, it's right. It doesn't make any sense. It was just complicated. It's just, very spaghetti in the past. I didn't know why I would allow these things to appear in the code. And then you start changing, and then you change one thing and change two things, and then you just look at the code. You're like, oh my god, how many do I have to change? And then I have to restrict. I can't change too much. And you change, and you're like, okay, now I think it's good. And you upload, and then iOS starts to complain, like, your certificate has expired. Your profile is invalid. Like, what the hell? They have to fix that. Oh man, it just all sorts of problems when you release. But as always, good, you do a better release before you do the actual release. All the problems you see now, so when the time comes when you have to actually publish the app in App Store or Play Store, and these things will not happen, hopefully. All right, anyway, we have to do today. So let's take a look. See that? Did you see that? Did you see that? Sudoku solver. I told you guys yesterday it's going to be Sudoku solver. I said it's a high chance it's gonna be this. And yup, we are here. I've done this before. Why is this what does this mean? Coding. Oh, okay. Anyway, so I told you guys, right? Because this is like a hint from yesterday that we probably would do this, and here we go. Here we go. All right. So honestly, I didn't really give too much thought, even though I said yesterday that it's very likely we're going to have Sudoku solver very soon as a hard question. But after I said it, I didn't really think about it. But now we are really dealing with this problem, and we can think about it very carefully. Now the good part, right? The good part is yesterday's problem prepared us for today in terms of how to verify that a value you put in there is going to be valid, right? It gives you that that thing, so it's good. So basically, if I remember correctly, I've done this one before. So if I remember correctly, we are going to do DFS with backtracking, right? So we're going to put in each values, right? Doesn't matter what value you put in. You put in each. So, well, first of all, you obtain um, the current status, the beginning status of each row, and then we're going to use the bit mask for this. So the beginning status of each row, each column, and each 3x3. So we obtain that already. And then for each position, we're going to just try a number, right? We're going to do a number from 1 to 9 and see if it doesn't match. We update it, right? And after we update, we move on to the next one. And we update, move on to the next one. Blah, 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 blah. We go all this, and every time we do, we check the row, we check the column. and then keep going, keep going, keep going. Once we fail, right? Once at certain position we tried all possible solutions, there's nothing matches, right? Then we have to return. Now, when nothing matches when return, then we have to backtrack. So the backtrack basically just we have to undo the row, undo the column, and undo the what do we call it? Undo the 3 by 3. Now, when we do, which is OR, when we undo, how do we undo it? Exclusive OR, right? We exclusive OR to undo because all we want is initially it's going to be a 1 bit, and we return that 1 bit to 0 bit, while others will remain the same. So we do exclusive OR. Yep, I think that's about it, right? Let's give it a shot. Oh man, I told you guys it's gonna be Sudoku. Well, actually, I didn't really say it's gonna be today. I just said yesterday that it's gonna be very likely we're gonna have it, but I didn't specify it's gonna be today. But I had a feeling. I mean, otherwise, I mean, it's for sure. I don't really think there is a person behind actually choosing questions every day. But I do think some people is monitoring this thing, right? So they probably have a random picker, right? Randomly is picking, picking the things, but they do not actually pick the things by random, but they observe it. Probably they say, oh, yesterday is a valid Sudoku. So how about we just do Sudoku solver? So they overwrite the random picking today and it becomes Sudoku solver. Anyway, so what are we going to do is we're gonna call it DFS. Let's call it DFS. Let's call it solver. I like to call it solver. We don't have to pass in anything. We need to produce 3 things. Rows, right? 0 times 9. Columns equals 0 times 9. And boxes equals 0 times 9. Right? And then solver. What is solver? What do we need for the solver? I and j, the position, right? We need I and j, which is the position. And this one will not return anything. We don't need to return anything. So when do we end? Well, we end when we succeed, right? Hold on. So we're gonna go row by row. Why don't we just obtain all the positions, right? And then we just iterate through these positions. Solver. So at each position, we're gonna check, right? We're gonna check just from 1 to 9, whichever is likely, we're gonna put it inside, and then we call solver on the next position, right? And then we call solver on the next position, next position, next position. And we can obtain all that How should we write this? Yeah, once we solve one, we move on to the next position. Next position that does not have a number. So, which means what we want is, to solve the next one, if I have a list of unknowns, right? And then I just go, hold on, we need to first obtain unknowns. This is going to be a list of positions, right? A list of ij, a list of positions. A row and column indices, right? And then for I in range 9, for j in range 9, what we're going to do is if board ij is equal to a dot, then we say unknowns dot append ij, right? Else we're gonna say rows I, this equal what do we call it? We call it mask. Mask equals 1 left shift int board ij. So this is the value, and then this is gonna mask columns j. This is to mark the starting position, right? And then boxes. This is going to be I divided by 3, and is that times 3 plus j divided by 3, right? I divided by 3 times 3 plus j divided by 3. So this is the index for boxes. So this one will all equal to mask as well. So we go through the initial to get the states of each row, each column, and each box. And then we're going to create a solver function, right? This is now we're talking about solver function. And we just need an index, right? Now we just need an index. So what we do is we're going to iterate through every single one inside unknown until we solve it. And for each index, we're going to have, so like if index is smaller than len unknowns, right? What do? So if it is smaller, then we have an index. So we have ij equals to unknown index, right? So for ij, this position, we try all possibilities. So for p, k in range 1 to 9, 1 to 10, so we have 1 to 10, so including 10, we have 9. So first we need to check a value is only possible if it has not appeared in rows, columns, and boxes, right? So we say if mask equals 1 left shift k, and we say if rows I and mask, if not, right, not this, which means hasn't been done before, and not columns I, columns j, and mask, and not boxes I divided by 3 times 3 plus j divided by 3, and mask. So that is a good. We have a good one. So if it's good, we're going to do it. How do we do it? Well, we are going to change the board, right? Change the board. So how do we change the board? We just say we're gonna do this, right? We're gonna do this. Boom. We're gonna do this, which is updating this, and then we're gonna say board, BORD, IJ, and equal to str k, right? And then after we make that change, we can do solver index plus 1. And this has to return a Boolean value. It has to return Boolean value. Which means if index is equal to len unknown, right? This one will return true. Because we, like everything, yeah. Now we do this, blah, blah, blah. So, solver just index plus 1. We go to the next one, right? And we say, if this is true, then we just return true, right? We solved it. Else, if it's not true, which means I pick this one is not true, then we have to backtracking. How do we backtrack? We copy all this, but instead of to OR, there's going to be exclusive OR. Right? We can use exclusive OR to return to the previous state, and this one will also return to the previous state. Which means this does not work. And then I check for the next. For the next. If I check everything, right? So if for this position, I checked for every one, and none of them work, then I return false. Because if one of them works, this one will work, right? Then I return false. So that's solving. And now we can call solver 0 and return no return. That's it, because it says they want you to modify the board in place. All right, let's take a look. I am not going to test because this is unnecessary. Let's just do it. Let's just put it here and see how it goes. If it doesn't work, we're gonna have to go back here. Yeah, I think it works. Yeah. Try it. Pending. Accepted. Yeah. I mean, the fact that I have done this before definitely helped. But the most important help is from valid Sudoku. The idea that we can use the bit mask to make the check much easier. Right? This check is so much easier. We get the state, and then we can assign the value to it, and then backtracking using very simple. And I think it's also very fast because we don't have to we definitely don't have to use this, right? We can use the hash map, the set, or the bucket method to do this. But then you have to iterate through them, right? So it becomes they are all one for all of them, but then you have to iterate through each one. So it's slower than compared to we just do the bit masking. The bit masking is definitely fast, right? It's very fast. All right, so I've done this before. I've struggled with this before. So I kind of remembered how this problem shall be approached. But the most help came from yesterday's problem, which um, which illuminated, right? Illuminates. I don't know, did I spell it right? How do you spell illuminate? Double L? Illuminate. It's not Illuminati. I just want to illuminate. Yeah, it's double L. It's double L. Say which illuminates the superiority of using bitmask to. I think it's called bitmap to check whether a value is feasible for a cell. Using bitmap significantly simplifies the procedure of validating a value and backtracking from a value. And the rest is a simple DFS with backtracking. No special tricks. Okay, I probably just add a little more context. I say this obtain the initial state of the board, and then we solve it, right? Runtime. Oh my god, I don't know the runtime. What is this runtime? I mean, everyone gets checked. You can call it ON, because at most every state got checked 9 times, right? Because for each cell you can check 1, right? And then you check 2, check 3, so every gets checked. Oh, but if I check 9 times, next one check 9 times, that's 9 to the power of something. So I don't know. What's the time complexity for this? I always struggle with backtracking on time complexity. Huh. Should be like, I don't know, man. Let's see the time complexity. Actually, I don't know the time complexity. I always struggle to find the time complexity of a backtracking problem. So I don't know. But this one runs. It runs. The runtime is 132 milliseconds, or it got an 80% ranking. Yeah, I mean, this is very straightforward, this solution, so I actually like it. And let's not have this. All right. 37, yep. I know it's number 37. LeetCode 37. When's the first time I do this? 2018. All right, so I started at 20. I think I failed. Look at this. I started at 5. 3 hours later, I think this. I checked the answer for this one. I think. Oh my. Oh my. Oh wow. Oh what the. Oh what the hell. Oh my God. Well, this is the evolution, right? You see this back almost 3 years ago, 219 lines, about 60 lines, 50 lines. Wow, that is, I am impressed about myself. Am I going to read this? No. Dear Lord, I'm not going to read this. But I am, I'm impressed that I was able to. Back then, I have much more time. This is all I can say. Back then, I have lots of time, so I was able to do something crazy like this. And another crazy thing is, right? You see this the first time I do it, and then 6 days later, I did it again. I don't know why. I don't remember why I did it again. This one is different. This one used the same idea now. Yeah, it's the same idea. You see, this is the exact same idea, but we use set. We use set for this. Yeah, we obtain the original state, I suppose. Actually, no, I didn't obtain the original state. But whatever it is, it's getting closer, right? Getting closer to the current. And then got some raw and got approved. Oh, this one's fast. 96. To memorize something, that's why it's fast. Huh. I mean, I don't know. Empty cells, yeah, I have empty cells, which is my unknowns, right? And then I append J. The empty cells to fill. I don't know. 6 test cases. How many test cases do we have this time? I think it's still 6. CPP. That's in November. I don't know why you even look at this. This is ridiculous. You're not gonna write CPP unless the job requires it. Doesn't matter. Right? Oh, I liked it in the past. Backtrapping with bit masking. Yeah, this is probably is the most efficient way. Boxes, backtracking, and true, empty cells. Oh wow, we might do the exact same thing. Box position for various. If blah blah blah, continue. Board blah 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 blah. If backtracking, return true. Blah blah blah. Return false. Yeah, that's exactly 9 to the m. Yes, I think that's. Did you say 9 to the m? No, I did not say. But yeah, it does make sense 9 to the m because 9 is each empty cell has at most 9 different, and then 9 to the m. Yeah, 9 to the m. Yeah. Use a lot. Yeah. Now this is that might be efficient, but this is the cleanest, right? The cleanest. Yeah. I'm almost exactly the same as this one. So update Here pit claims that the time complexity is 9 to the m, where m is the number of unknowns, the length of unknowns. It makes sense. Here is his post. The size. All right, let's check the other guy. He always writes something shorter, something more provocative. MT for dig dot add. That's the default dict. Nah. I think it's about the same. You just use default dict and I set. No, that's the same thing. It's about the same thing. It removes. Yeah, this one says 01, so yeah, we can also say 01. Yeah. The Babichev, right? Babichev claims that the time complexity is 01. Oh, I should say O. Which also makes sense. Also makes sense because we know the upper bound of m. We know the upper bound of m. Here is his post. Doesn't matter. I mean, we solved it, and then yeah, I can say confidently that I'm not afraid of this one anymore. I used to be kind of dreading this, but not anymore. Alrighty, I think that's it for today. Oh, I think we dodged a bullet. I mean, if it's a real tough question, it won't be that easy. I mean, because I solved it many times, that's why. I'll see you guys tomorrow then. Adios.